the recording. Okay, so do you have any question before we starting? Okay, if not, then I'm gonna start from this slide. So lovely, let's go back one slide before. So in the last class, I discussed about assumptions for ideal p-n junction diode. So in the following slide is actually based on this assumption we discussed in the last class. I'm going to derive the equation for the p-n junction diode. Okay, that's what we're going to do today. Okay, so the first is that we have to understand this terminology is called the low-level injection. Okay, so when you say the low-level injection is, for example, let's say if you have semiconductor, which is the N-type silicon. Okay, so to make the N-type silicon, as you know, is we dope the silicon with a donor. Okay, so when we doped with a donor in the silicon, now is that from in here is that we get the N-type silicon. So for the N-type silicon, we have the majority carrier, which is defined as the electron, and the minority carrier is we define as the hole. Okay, and then this number of electron is we assume is close to the doping concentration. Okay, now number of hole, this is the minority carrier concentration. This one is we calculate from the Ni square divided by Nd. Okay. Now these two, majority carrier and the minority carrier in here, the concentration of these two, at this point, this is at the thermal equilibrium. Okay, so which means that from outside, we do not apply any bias or any external energy is not applied to this material. Okay, so at thermal equilibrium, as you know, the majority carrier concentration and minority carrier concentration, you can calculate from their doping. Okay. Now, in here is that when you talk about the low-level injection, the low-level injection, the condition, this one is, what you, as you can see in here is you have a majority carrier and then the minority carrier concentration. Okay. When the minority carrier concentration is much lower than the majority carrier concentration, that's the condition we define as the low-level injection. Okay. Especially this one happens when you have the p-n junction diode, p-n diode, and then when you apply the forward bias, which means that in the p side you apply the positive, n side you apply the negative. When you apply the forward bias, then as you see is that the hole is start to diffuse to the n side, electron diffuse to the n side, p side. Okay, so this kind of process is the hole moving to the n, electron move to the p. This one is we can treat as the injection. Okay, when this injection happens, especially at the edge of the depletion region, let's say this is the depletion region. At the edge of the depletion region, your minority carrier concentration start to increase. Okay, So which means that in the N side, minority carrier concentration, this one going to be whole. Okay. So whole concentration at the edge of the depletion region start to increase when you apply the forward bias. Okay. Now, the level of the minority carrier concentration is lower than the majority carrier concentration. That's the condition we define as the low level injection. Okay. In the following slide, I'm going to also show the detail of that concentration when you apply the different bias. Okay. So, but at this point, that's the definition of this low level injection. Okay. In here is that especially when you apply the bias, we follow this derivation and then correlate the whole concentration or electron concentration at the edge of the depletion region. Okay, so at the thermal equilibrium, as we discussed, VBI you can calculate from this equation, KT over Q, Ln POP means this is in the P side, your whole concentration at the thermal equilibrium. Okay, that's the meaning of this POP. PON, this means is in the N side, whole concentration at the thermal equilibrium. Okay, that's the meaning of PON. So using this equation, you can calculate this VBI in here. Now, from this equation, if we apply the bias in the PN junction diode, the applied bias goes to the junction, and then the junction voltage we can rewrite with this equation. Okay, so instead of VBI, we add VBI minus VA. VA is the applied bias in the outside. Okay, that goes to KT over Q. Now Ln in here is the same expression, but in this case is we can just put the whole concentration in the P side, okay, on the top, and then on the N side, whole concentration using this equation. When you apply the bias, now it's not thermal equilibrium, okay, so that follows this equation in here, okay. And then now in here is that if we look at the whole concentration at the edge of the depletion region, the P side, that will follow this equation in here. So if you look at this equation in here, that equation is just coming from the top in here, okay. So we rewrite this equation in terms of this whole concentration in the P side, okay. Then you get this equation, and then the VBI is we just use the equation in here, okay. So now is from this equation is that we have this following equation, okay. So this term is go same way in here, okay. Exponential Q VBI KT, that's going to be this one, okay. And then the remaining, this one will be same with this equation, okay. So we have this equation in here, okay. Now, in here is that we're going to rewrite this one in terms of the whole concentration at the edge of this depletion region in the N side. Okay. There will be in here, if we look at in here, there will follow this equation. Okay. So to get this equation, we get this condition in here. The condition this one tells us is a p side hole concentration. P side hole, this one meaning majority carrier in the p side. That follows that the majority carrier concentration in the p side at the thermal equilibrium. Okay. So this condition we follow based on the low level injection. Okay. So at the low level injection, the majority carrier concentration still remain as your thermal equilibrium value. Okay. So that's the meaning of the low level injection. And then based on this low level injection, you get this kind of a conclusion. Okay. So if we draw this conclusion in terms of carrier concentration, we get this kind of graph. So this graph shows that especially minority carrier concentration, so which means in the p side, minority carrier going to be electron, okay. N side, minority carrier concentration going to be hole, okay. So first, at the thermal equilibrium, which means there is no bias, the hole concentration in the p side, in the p side, the electron concentration will follow this line. Okay. In the N side, minority carrier concentration follow this line. Okay. And then this is at the thermal equilibrium without any bias. Now, in this condition is we apply the VA. Okay. So in the PN junction, you have P, and we apply the VA. Okay. So when you apply this VA in here, let's go back previous slide. We get this conclusion in here. So which means in the N side, your new hole concentration will follow this equation. Okay. If we look at this equation carefully, this hole concentration will follow from your thermal equilibrium value multiply with the exponential QVA over KT. Okay. So in terms of a graph, in the N side, this represents your hole concentration. Okay. Now, when you apply the bias at the edge of the depletion, which means that at the XN location, your concentration going to be increased. Okay. And then that increase of concentration will follow this equation. Okay. So which means that your thermal equilibrium value concentration multiply with exponential QVA over KT. Okay. So that conclusion we can get from this graph in here. Okay. So same way, if you look at the P side, based on the same approach, in the P side, your minority carrier concentration going to be electron initially, okay, and the electron concentration follows this line, okay. Now, when you apply the bias, VA in the PN junction, the concentration going to be increased, okay? And then that number going to follow this equation, okay? So from NPO, which means that the thermal equilibrium value, multiply exponential is QVA over KT, okay? So that's the new value when you apply the bias in this junction, okay? So that way, so you can calculate this concentration in here, okay? So now, before we move to the next slide, I have a question for you, okay? So for example, let's say if I draw the minority carrier concentration such a way showing in this graph, you have a P side, N side, and then you have a minority carrier concentration level show this way, okay? Now, my question in here is, if you just look at this distribution of minority carrier concentration, okay, throughout this X, right, in the PN junction, which side, either P side or N side, which side from this graph showing more doped? So can you tell?
Yeah, Professor.
Okay.
So P side is the more doped.
P side is more doped because
it's forward biased. And it is forward biased, and as well as if we look at the N side, we see the minority carrier is higher than the line of my minority carrier is higher than the minority carrier on P side.
Yes, so that's correct answer. So if you look at the minority carrier concentration level, so as Mohammed mentioned, is that this side is lower than this side, right?
Yes.
So which means that your doping level is the P side is higher than the N side from there, right? Okay, that's good answer. And then the other thing is that, as you can see in here, is now, if I give you that the bias, right? If I give you the bias, then you can actually calculate the carrier concentration, especially minority carrier concentration, at the edge of the depletion region, right? So using this equation. Okay, so that is also is an important concept. Okay, it's good. Now in here is especially this one shows that in the forward bias. Okay, you have a P-N diode, and then this green area represent the depletion region. Okay. So when you look at the PN junction in this way, okay, and then when you apply the bias in the outside, most of the bias at this ideal PN junction diode is, as we discussed, is going to this depletion region. Okay, so which means that we can effectively saying that the electric field throughout this PN junction diode, effectively electric field is only exist within this depletion region. Okay, and then we can almost ignore in the bulk region, P side, N side, electric field is going to be minimal. Okay, so that's the first you have to understand. Move to the next. Okay. Now is our interest in here is so far is, as we discussed, When you apply the outside is the forward bias, for example, in the PN junction diode. Okay. So when you apply the forward bias in the PN junction diode, I can certainly ask at the depletion edge, what will be their minority carrier concentration, right? So when I ask this one, so for certain doping and then the bias condition, you are able to answer that question based on the previous equations, right? Now, our interest for next is we know that there's a minority carrier concentration in here. Then now is that we want to see this minority carrier concentration, how this one going to change within this bulk region. Okay, so that will be our next the question in here. Okay, so to answer this question is that in the semiconductor, we need to solve the two semiconductor equation. Okay, and one is we call the continuity equation. Okay, another one in the semiconductor is called diffusion equation. Okay, so by solving these two equations, we can also calculate current throughout the device and also all the carrier concentration throughout the device. Okay, so that we can calculate using these two equations. Okay, now if you look at this equation, continuity equation, diffusion equation also separate into the electron case and hole. Okay, so same way. Okay, if you look at the continuity equation, for example, let's say in terms of hole, continuity equation tell us the concentration change of the hole in the small piece of semiconductor. So for example, let's say if you have a small piece of the semiconductor, okay? Now, let's say this is the Tx amount of this separation in here. In here is our interest is inside of this material, our interest how this whole concentration changing in terms of location X and then in terms of time. Okay, that's our interest in this material in here. Okay, now this change in here, if we formulate this one, that change will follow this equation in here. Okay, so if you look at the equation carefully, equation tell us in terms of whole concentration change in terms of time. Okay, so in terms of time, any kind of whole concentration change coming from the first injection of the current into the material, which represent by the current is JPX in here, and then the current coming out in here is JPX plus dx. Okay, so if we inject the current by applying the bias, okay, into this material, semiconductor material, that will change the whole concentration within this material. Okay, so that's the first concept and the first term of this equation. Okay, and then another term within this material, if the material support generation, then that will also change this concentration. Okay. Negative, this all represent the recombination. Okay. So generation, recombination, that will also change the concentration of this hole. Okay. So generally, at the thermal equilibrium, generation and the recombination, they are balanced. So we do not see any change of carrier concentration from this generation and recombination. Okay. But if material somehow is concentration of, let's say, hole, for this case, is more than their thermal equilibrium value, then now, as the time goes, material try to go back to thermal equilibrium value. Okay, so for that case, this balance between the generation and recombination going to be break. And then, in this case, if you have more holes, for example, in here, then from the recombination process, the whole concentration is going down and then reach to the thermal equilibrium value. Okay. In other words, if the material has the less concentration than its thermal equilibrium value, then now for that semiconductor area, promote the generation process. Okay. So you have more generation happens there, so that eventually semiconductor try to go back to their thermal equilibrium value. Okay. So using this kind of process, we can actually tell is that any change of this concentration in the piece of semiconductor, either hole or electron, coming from either current injection through the material or generation or recombination process. Okay, so that's the meaning of this continuity equation. Okay. Another equation, this one is we call the diffusion equation. Okay, so diffusion equation is simply tell us about the total current contribution from this semiconductor material. So for example, if we look at the hole, for example, total hole current is coming from the first part is drift current. Second part, this one from the diffusion current. Okay. Drift current, this one, as you see in here, they're related with electric field. Okay. And then number of hole, and then their mobility. Okay. So if we multiply this term in here, that gives us the drift current. Okay. Diffusion current related with the concentration difference. So in the space, if you have the change of concentration, that gives us the current flow. So, and then that follows the diffusion coefficient. So this coefficient shows how fast this diffusion happens in the material. So using this equation, you can calculate the diffusion current. Okay. So if we add the drift current, diffusion current, that gives us the total current. Okay. So this total current is now in here is described as the diffusion equation. Okay. So similarly, we can also put the electron current that coming from the drift current and the diffusion current. Okay. That tells us now is a diffusion equation. Okay. So any kind of semiconductor device, when we look at their concentration change and then current flow when you apply the different bias in the material. Each material, they follow these two equations, okay? And then we need to solve these two equations to get those information, okay? So if you look at this equation carefully, now, for example, let's say electron case, okay? Electron current related with electron concentration in here, okay? Now, if you look at the continuity equation, the electron concentration also related with the current, okay? So, which means that now these two, they are actually coupled together, okay? So, when we solve the semiconductor equation for the given domain of the semiconductor, we need to solve these two equations at the same time to satisfy this coupled equation. Okay, so sometimes that makes a little bit difficult to solve this semiconductor. Okay, okay, so that's the one thing. Now, in here, as the very simple example in this slide, I'm going to just look at the very special case to solve this continuity equation. Okay, so for this example in here, I'm looking at in the N side, N region, the holes. Okay, holes in the N region represent the minority carrier concentration. Okay, in the N side. Now, for this case, to solve the continuity equation, okay, especially for the hole, the first is the continuity equation. We just copy from the previous slide. Any hole change in terms of time coming from the current and then the generation and recombination. Okay. So that's the general equation for the continuity equation. Now, in this continuity equation, we're going to actually apply some simplification, especially for this particular example. In this case, first, we're going to only look at the one dimension. So again, in here is in the real semiconductor, as you know, is a semiconductor device following the three-dimensional case, right? So we have to solve the X and then the Y and then the G direction, okay? So these all direction coupled together, so which makes it's much difficult to solve in the multiple dimensions, okay? But for this example, we're going to just look at only 1D case, okay? So in the only X, okay? So for this case, that's the first one, 1D case. So we only look at the X direction. And then second one is, let's look at steady state case, okay? So steady state case means that, let's say if you have the PN diode, okay? I'm just applying the constant, the voltage, without changing the voltage in time, okay? So that means in the steady state, okay? So when the steady state, as you can see, now time variation going to be 0 for our case. So which means that in the continuity later on, this time variation of the whole concentration going to be 0. Okay, so that's another simplification in here. Okay. And then the current. Okay, so when you look at the current, as I mentioned, is that in the diffusion equation, okay, whole side, total diffusion equation, the whole current is coming from the drift current plus diffusion current. Okay, that's we know is from the previous equation. Now, In here is that especially we are interested for this particular case, we are interested in the holes in the N region. Okay, so N region means that in the bulk N region, which means if you look at the p-n diode, okay, this is the depletion region. In the N region, we are interested in this N region. Okay, so that's the meaning of these holes in the N region. For this case, is as you discussed in the previous slide, when you look at the current, now this N region in here, the total current, this one is effectively, we can say that that coming from the diffusion current. Okay, the region is in the N region, bulk N region, your electric field going to be 0. Okay, so there is no electric field in the bulk region, so which means that you do not expect to see the drift current. Okay, for this case. So that area is now is that is the current, this one. That current is, if you go back, is following this equation. And then because this is close to 0, so we can disregard this drift current. Okay. So instead of JP, now is, so we're gonna add this equation. Okay. So if we do that one in here, just 1 second. Oh, okay. Now is that this equation is, as I mentioned, this term going to be 0 because of steady state. And then JP, we replaced with a diffusion component. Okay. So this one is, diffusion component is minus Q, and then dP, dx, dP, right? So if we plug in that one to this equation in here, okay, and then the multiply with this Q, all the place, then you have this one, okay. And then another term is that this term, okay. Generation and recombination, as I mentioned, at the thermal equilibrium, they follow together. But in here case is that we apply the forward bias, okay, so that you're gonna start to inject more carriers in the N side. So which means if you look at the carrier concentration in the N side, this is the, let's say, N side. You have hole, PON. If you apply the bias, hole concentration in here is increased. And then this increases this one, following that the PON exponential QVA over KT, right? So we have the increase of this carrier concentration. So in the bulk region, we expect that as you go into the bulk region, that goes to the thermal equilibrium, okay, by promoting the recombination process, okay. And then this recombination process in the bulk region is now we can rewrite with the so-called carrier lifetime in the hole, okay. So that one is we can rewrite with this equation, okay. So in here is the P represent your hole concentration minus PON represent at the thermal equilibrium hole concentration. So P minus this one represent any excess hole concentration, they will decay with this tau p. Okay, that represent this generation and recombination process. Okay, now our question is now solving this equation. Okay, so if we look at this equation, that equation is kind of we can solve is easily. So in here is that as a trick, instead of this excess whole concentration, okay, we can put this one as the prime of the p, okay, and then this is anyway is a derivative, so we can just put the p instead of p, we can just p minus p o n. So we can rewrite with this one, with this equation. Okay. So now, if you look at this equation, is that the p prime, if we do the second derivative in terms of this x, that gives us the p prime itself with a certain coefficient. Okay. So to satisfy this equation, only equation satisfying this one, following the so-called this exponential term. Okay. So if we just simply assume the solution of this p prime with p1 and the p2, that's the coefficient we need to find from the boundary condition. And then exponential in here is LP, represent actually this term. Okay, so based on this definition in here, we put that one in here LP. Then now you can get the whole concentration as a solution following this equation. Okay. So now remaining thing is to solve this equation is we need to solve P1 and then P2. That's the coefficient which we need to find from the boundary condition. Now, boundary condition in here, to solve this equation, we have the two boundary condition. Okay, so one is, as we discussed, so in the n side, at the thermal equilibrium, whole concentration is, let's say, if we put the PON as the line in here, okay, and then this is the depletion edge in the n side, okay. Now, at the depletion edge, if we apply the forward bias, the concentration from the PON, they're going to be increased to the new value, okay? And then this new value is, as we discussed, going to be PON multiply exponential QVA over KT, okay? So now that serves as the one boundary condition, okay? So boundary condition one will follow this one. So which means that in here is the x prime, this one is actually, we put from this definition in here, okay? So which means that when the x equals xn, x prime, this one goes to 0, right? Okay. So which means that when the x prime equals 0, the boundary condition of the p prime, this one represents p minus PON, okay? That will follow now is the equation in here is this one. So which means that the P, new P, will have this equation. PON is the same way using this equation, okay? So that solves as the first boundary condition. Now, second boundary condition is when the whole concentration, whole injected to the N side, and then when this one moves to the inside the bulk of this N region, the concentration of hole going to be decreased. Okay, and then eventually is that reach to the thermal equilibrium value. Okay, so which means that let's say if this X prime going into the infinite, okay, we expect that your hole concentration reach to the PON. So which means that in terms of P prime, this one going to be 0. Okay. So these two boundary conditions we can apply to obtain this P1 and then P2. Okay. So if we apply that one, is these two boundary conditions in here. The first one is the X prime equals 0, which means that in here. And the second one is X prime goes to infinite, or in our case is in here is, let's say if you have the PN diode, okay, and then this is a depletion edge. At some point is that at the edge of this N side, you're gonna make the electrical contact, the metal contact to the outside. Okay, the metal itself has the large number of electron holes. Okay, large number of electron holes available. So any excess in here is the hole in the N side. When they reach to this metal, that instantly going into the thermal equilibrium value. Okay, so which means that when the X prime that equals to Wn, which at the location of this metal, we expect that this excess hole concentration going to 0. Okay, so if you apply these two boundary conditions, then now you have this condition in here. Okay, so one is that at the X prime equals 0, okay, in the solution, if you put the 0, then you will get the P1 plus P2. Okay, that equals this one. Okay, so which means that's this equation. Okay, and then second boundary condition is when you apply the hole concentration at the location of the metal contact in the N side, that's going to be 0. Okay, that gives us another boundary condition. Okay, so if we apply these two boundary conditions, and then we have two unknown, so correlate this equation, then now we can obtain this P2 and then P1 coefficient. Okay, so then now is we have the complete this equation describing this hole concentration. Okay, so excess hole concentration now follow this equation, exponential equation. Okay, and then the P1, P2 coefficient that follow this obtained this equation. Okay, so using this approach is now you can obtain this concentration of the hole in the N side. Okay, so if we rewrite and then as a general solution, if we write the hole concentration, excess hole concentration will this equation. Okay, so that's the meaning of this hole concentration in here. Okay. Now, before we move further, is the equation hole concentration, excess hole concentration. We look at the two extreme case. In terms of Wn, Wn is again, as I mentioned, is now we are looking at this configuration. This is a P, this is N. You have a depletion region existing here. At this point, our interest is in the N side, hole concentration. Okay. So in the N side is that, let's say this position is the X prime equals 0 position. The position in here that represent is that the X prime equals WN. Okay. That's the metal location. Okay. Now, in here is that as the two case, we compare the value of Wn, and then another one is we compare of the LP. Okay, the LP, this one is we call the diffusion length. Okay, we call this one as a diffusion length, LP. And then as I mentioned, this one is defined by the two parameters. One is a diffusion coefficient, and then this one is a carrier lifetime. Okay, especially P represent the whole lifetime. Okay, so if you have this square root of dp and then the tau p, that represent the LP. Okay, and then in the exponential term, if you look at the carrier concentration in here, the LP represent is when the X, this one is from the depletion edge to the this location. And so this X prime is increased. Okay, depends on the LP. If we have large LP, okay, the change of this exponential term is affected by this LP. Okay, so LP represent that kind of coefficient. Okay. So now is that in these two cases, we compare this Wn and the LP. So first case is when the Wn is much larger than the LP. Okay. Wn is again, this is the location of this metal contact in the N side. Let's say that is the much larger than the LP. Okay. So for this case, original equation is the solution we obtain. If you look at this one, this is the solution we obtain in here. And then if you look at this solution, at some point is that we have Wn, LP, they are compared in the equation, right? Now, depends on whether Wn is much larger than the LP or Wn is much smaller than the LP, this equation can be simplified. Okay, and then that simplification is we follow this equation in here. Okay, so if we follow this one is the first is if the Wn is larger than the 3 times of LP, we can approximate this equation with this term. Okay, and then from there is that now is that we have the solution for this excess hole carrier concentration. We'll have this kind of equation. Okay, in other words, if we plot this one in the N side, this is the X, and then carrier concentration at the Xn in here. You have excess carrier in here, okay, and then that one is coming from this equation, okay, and then that one is as we go from the Xn to this contact region, that one is exponential decaying like this. Okay. So depends on this LP is now this decaying is that like this, or it can be very abrupt like this. Okay. So that kind of change is you can see from this equation. But anyway, in this Wn is much larger than the LP, our carrier concentration will still follow this exponential term. Okay, so that is the first conclusion in here. Second case is now is Wn. This one is much smaller than the LP. Okay, so in other words is that if you look at the n side, the Wn, this is very close to this junction edge in the n side. Okay, so in this case is that from the general equation, this one, if you apply this special case, then our final carrier concentration is approximate with the linear equation in here. Okay. So which means that when you look at the carrier concentration, now this is the x prime. Initially this is the 0. Now the carrier concentration is almost linear. Okay, so linearly change like this. Okay, so when the Wn is very close to this junction. Okay, so that give us the final solution for that specific case. We have this equation. Okay, so in summary is that this one tell us depends on the location of the Wn. If the Wn is very far from this junction, then carrier concentration is still following the exponential decaying. Okay, but when the Wn is very close to junction, then that decaying is almost linear. Okay, so these two special cases, we can have this particular solution for this minority carrier concentration. Now, similar this concept is we can apply to the P side. Okay, so far is that as we discussed, this is a P, this is N, this is a depletion region. The previous slide is we discussed about in the N depletion edge, how this minority carrier concentration in the excess minority carrier concentration going to be changed within this neutral region. Okay. Now, similar concept is that we can apply to the P side. Okay. So P side minority carrier concentration going to be electron. Okay. And then excess this electron concentration. If we apply the similar concept, then we can have this kind of general equation. This general equation again is this one represent when now is the contact in the P side is very far from this depletion edge, then carrier concentration going to be changed with this exponential term, with this Ln, right? So that represent now excess electron concentration in the P region. Okay. So this is the kind of summary what we did so far. Okay. So we are interested in here is called the coercive neutral region. In other words, especially in the bulk region, either P side, N side. Okay, we are interested in the minority carrier concentration. Okay, so in the N side, the minority carrier going to be whole. Okay. In the P side, minority carrier going to be electron. Okay, And then when you plot this carrier concentration from the thermal equilibrium value, we can have this kind of exponential decay when you apply the forward bias. When you apply the reverse bias, okay, now your carrier concentration is actually lower than your thermal equilibrium value. Then from there is that you'll get the increase of this carrier concentration and then reach to the thermal equilibrium value. Okay, so we can have the general this kind of carrier concentration change when you apply the forward bias and then reverse bias. Okay, and then this graph is actually summarized these changes of carrier concentration. Okay, and then the detail of the change of this one following these two equations. So again, this is a summary. So when there's no bias applied, okay, there's no bias applied. If you look at the P side you have a majority carrier and then minority carrier, okay, and then you have a depletion region, okay, and the N side you have a majority carrier and then the minority carrier, okay, and then their carrier concentration follows this straight line, okay, from the outside of depletion region. Now, when you apply the forward bias in the p-n junction, the forward bias make the barrier height between the p-n is lowered, okay, and then this lowered barrier height promote the diffusion, okay. So in other words, the p side, the hole is moving to the n side. So if you look at the carrier concentration now in the n side, because the hole is moved to the n side through this depletion region, your carrier concentration of the hole is increased at the edge of the depletion region. Okay, and then if we go deep in the semiconductor, that promote the recombination process, and then that going down, 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 eventually that leads to the thermal equilibrium value. Similarly, in the n side, you have larger electron, and then by applying the forward bias, barrier height is decreased. So now electrons start to diffuse to the p side. Okay. When the electron diffuse to the p side, at the edge of the depletion region, your hole concentration is increased, coming from the thermal equilibrium value. Okay, and then if you go deeper inside the P, now this concentration is decreased, and then eventually that leads to the thermal equilibrium value. Okay, so that happens in the this forward bias. And then if you apply the reverse bias, as you know, concentration is decreased. Okay, and then if you move deep in the material, now generation is dominant there, and then that creates the carrier concentration change is this way, and then leads to the thermal equilibrium value. Okay, so that way is now we can look at this distribution of the especially minority carrier densities at the various this applied bias on p-n junction diode. Now, next one is we are interested in the current. Okay. To look at the current is now is as we discussed. The current, for example, is a hole current. Is coming from the one is drift, and then another one is diffusion. Okay. Now, to calculate the whole current, in the previous slide, we obtained the whole concentration, right? Now, especially in the neutral region, as I mentioned, electric field is almost zero. So we can expect to delete the contribution of this drift current. Okay. So only current is now limited by the diffusion current. Okay. So diffusion current equation is, if you go, then that follows this equation. Okay. Again, as you can see, this diffusion current related with the whole concentration change as a function of this P. Okay. So in the previous slide, we obtained this whole or excess whole, this concentration as a function of this X. So if you plug in that function in here, then now is you can obtain this kind of equation. Okay. And then in here is we split to the two special case when the Wn is much larger than the LP, 1. Then whole current will follow this exponential term. Okay. And then when the Wn is much smaller than the LP, then whole current is following that linear equation. So if we do the derivative of this one, now whole current will have this one. Okay. So we have this whole current calculate from this equation. The slide in here is the important thing is when we calculate the whole current, especially in the neutral region, we just need to use this diffusion equation. Okay, diffusion, the current equation. So using this one is you can calculate this whole current. Okay. So similar approach we can apply to the electron current in the p side. Okay. So if we apply that one is, for example, is for this particular case, Wn is much larger than the LP, which we expect that that follow that exponential decaying. Then you have Jp and Jn, so you get this one. Okay. In here is especially we apply the location. Jp is that when the x equals xn, so which means that this is a depletion edge, you get this current. Okay. So in other words, in the previous equation in here, okay, so Jp, especially Jx prime equals 0, okay, exponential term, this one going to be 1, so you only have this term. Okay. X prime equals 0 means that the x prime we define as the x minus xn, right? So that's the depletion edge. Okay. So from there is now is you get the xp xn, especially at the depletion edge, you get this equation. Okay. So now if we look at this current in here and the plot, I will go back this one, you will get this kind of curve. Okay. In the n side, if you look at the whole current follow that the initial, when the x equals xn, you have value, and then that exponential decaying like this. Okay. This curve, as I mentioned, following that this one. Okay. So when this special case, okay. When you plot this one, okay, that one is more abruptly changed in here. Okay. So anyway, is that represent this xp. Okay. Now, in the similar way, if you look at the electron current in the p side, you have initial value, and then the exponential decaying like this. So from our approach, we obtained these two current. This represents the minority carrier current. Okay, in the N side, hole current, P side, electron current. Okay. Now, in here is that we applied our assumption. Okay. One assumption is when we discuss about this ideal p-n junction diode, especially in the within this depletion region. Within the depletion region, okay. So this within this depletion region, in here is that we assume that there is no generation and then no recombination happens. Okay. So which means that any electron going into this depletion region, eventually that comes out from the other side. Okay. Any hole is going into this depletion region, that eventually coming out. Okay. So we do not lose any charge, or at the same time, we do not generate any charge in here. Okay. So that assumption gives us the current within this depletion region remain as the constant. So which means the whole current is the depletion edge in here, in the N side was in here. So that remained within the depletion region as this value. Okay. So same way is that if you look at the electron current, okay, electron current depletion edge in the P side was in here, and then that remained as this value. Okay. So that way is that you have the electron current, hole current is represented in the p-n junction diode. Now, when you look at the total current, okay, total current is coming from you have electron current plus you have hole current. Okay. So simply within the depletion region, if we add these two, then that gives us the total current. Okay. Then throughout the p-n junction is just a single this device. Okay. So your total current is going to be constant throughout the device. So you can have the constant, this total current, following this total current in the depletion region. Okay. So that way is that we can obtain the current in the p-n junction diode. I guess we have 3 minutes left. Do you have any questions so far?
Since the hole current and the electron current, they go in different directions, do you have the magnitude or do you do the difference?
Oh, the hole current and then the electron current, they are not actually going into the different direction. So as you, this is the, for example, this is the forward bias, right? So as we discussed in the forward bias, PM, VA, the hole in the P side that moves in the N side, right? Okay, so when this one is hole moved in the P to N, your hole current is that in this direction. Okay. In the electron, this one is that the electron moves the N to P. Okay. When you look at the electron current is the opposite direction of the electron. So your electron current is same direction to the JP.
Oh, yes, I remember. Thank you.
Okay, okay, that's good. Any other question? So in the next class, I'm gonna briefly again review this procedure, but I'm hoping that this kind of thing is already covered in 339, so you can understand this procedure without any difficulty. So, any other question do you have? Okay. Okay, so if you do not have any other question, then we're gonna stop today's class in here. Okay.